And then when we get the counts, we have a whole series of, everybody has seen, I guess, a gamma ray peak. I'll just show from some NIST work what a palladium gamma ray looks like for palladium 105, and this is the one I'm choosing because it's so clean relative to all other gamma rays in the system. And unfortunately, boron has a not quite so beautiful peak because it's Doppler shifted, because the captured gamma ray captured in boron 10 results in alpha plus lithium 7, and it has a long enough lifetime to be Doppler shifted by about 20 kilovolts. Furthermore, the palladium has a few gamma rays that overlay this in such a way as to, so if you had pure boron, just with a little sodium impurity, this is what it would look like. It would be a very flat, 20 kilovolt wide, so-called peak. And this is, of course, a sodium peak, which is not in my samples. I know where that's from. It's the sodium iodide complement suppression annulus. Anyway, so it's not a quite ideal system, but it's what I had. So we integrate the charge, or I should say the counts, under those peaks, and use that as the quantitation for these various gamma rays, and calculate then the ratios between peaks from neutron captured gammas in each different isotope present in each sample. And the ratios are within the sample so that I'm not subject to so many uncertainties of how I prepared the sample or the conditions of the radiation. And I compare the ratios between the virgin and the active cathode. And if I see any changes, and by the way, I haven't looked at all of the possible changes in these. I've just chosen one hypothesis to check. And I put just at boron 10 and palladium 105. So if I see any changes, maybe that's indicative of the excess heat, just to show the kind of setup you have. A neutron beam, and off to at 90 degrees, you see the detector. And of course it has gamma shield lead as well as the annulus for the sodium iodide Compton suppression anti-coincidence annulus. So here's my measurement of it, of the palladium 105 capture gamma ray at 616 kilovolts, and it's very clean. And here's the virgin material, which has 4,173 integral counts, and the active cathode with 12,151. And as you can see, one is quite a lot bigger than the other, but that's just an accident of the fact that I happened to take a mass, 3 times the mass of the active cathode as I had for the virgin. But that was arbitrary and not of any consideration, since I'm going to do the ratio between that and the boron 10 in the same sample, and this one, the boron 10 in that same sample. So that mass change should cancel out. Now here's my measurement of 3, it's not so clear perhaps, but 3 different, this one. Anyway, we have 3 different, the active cathode at the top. I have the sodium peak that have to shave off, and the integrals are shown, the virgin material and finally the background. And since I have, okay. The background is appreciable, but nonetheless I have to subtract it from the virgin and subtract it from the cathode to get the net. In the case of the 616 kilovolt gamma ray palladium 105, there was no such background because in that particular region, nothing was giving us anything in the way of background that I couldn't already subtract out by shaving the bottom of the peak. Okay, well here's the ratios that we can obtain for this particular run. And by the way, this is the second run I've done on this. As you can see, we had about 20,400 interval counts subtracted from the background 10 for a net of about 10,000. And virgin had 14,600 for a net of 4,200. And you can see these are not so accurate as you would like because of the strange shape of that overall sort of modified square peak of boron 10. In the case of palladium 105, I have some very good statistics here. Not quite that good, but at least much better. And with a nil background, the nets are here. So we do the ratios, cathode net to boron 10 to palladium 105, and you get a ratio of 0.882. And the net for the virgin is 1.01, or about an 18% drop. Boron 10, or a burnout, you might say, of boron 10, or a loss of boron 10 relative to palladium 105. And the uncertainty, of course, is uncomfortably large, but nonetheless, I make a point down here that 8.82 may be an upper limit due to the dilution effect of a couple of palladium captured gamma rays within that boron 10 Doppler broadened peak, which I know are there from the literature. So, indeed, I think we have a suggestive, if not definitive, result. Now, conclusions. The analysis of the C2 cathode by PGA, that's prompt gamma activation analysis by thermal neutron capture, shows about an 18% depletion in boron 10 relative to its concentration in the original unused cathode foil, which, by the way, was about 1 mil or 25 microns thick. If the boron 10 D-alpha reaction to make beryllium 8 going on to 2 more heliums reaction were the source of the 0.56 megajoules observed during the 356-hour life of this cathode, then guess what? We would expect about an 18% boron depletion. I've never been that lucky in most of my experiments. So naturally we've got to be a little suspicious of it. And so a conventional explanation of this depletion involves the possible selective chemical leaching of the boron content by the 1 molar lithium deuteroxide electrolyte during that 356 hours. And I'm in the process of checking that question by running the anode, by the way, which is the same material and would be subject to dissolution of the same sort, perhaps even more, because being an anode, and that test is currently underway. Thank you.
Thanks, Tom. We have 10 minutes for discussion, please.
Just a curiosity, why did you check only the 105?
Pardon? I didn't understand.
Why did you check only for PD 105 and not the other?
It was convenient. I thought that it was unlikely that we were burning palladium 105. It had a gamma ray completely separate from all others. It was clean, and it was relatively abundant. All those features.
Also PD 108.
Yeah, I could have chosen a number of others, and I had a choice of maybe 20 or 30 gamma rays, and so it was an absolutely arbitrary choice. And if palladium 105 is being burned, then I'm off by some number here, but my previous work showed that we weren't seeing very much change in the ratio of various palladium isotopes, more than about 3 or 4%. So that I thought I was safe in choosing palladium 105.
Please. Yes.
Okay, if I well remember, at the beginning of the cold fusion experiments, people from naval fission laboratory, Deborah Robinson, found some isotopic shift in palladium used to give positive ray inside. There is some correlation between your results and the old data of Robinson?
Of who?
Deborah Robinson, Naval Fission Laboratory, Washington. Did you watch?
Ross.
The experiment made from Deborah Robinson in Washington in 1990 about. She found some strange isotopic shift of palladium that give.
And one of the palladium isotopes?
Yes.
Yeah. There could be
And
still.
the depletion, so okay, similar.
Well, the beautiful thing about this system is that it is not subject to the problems that the SIMS has, time-of-flight SIMS and the SIMS, because it's looking at a tiny little spot on the surface. And you might need the entire GNP of the country to fully characterize every spot on the surface of a cathode, and also versus depth. So that this method sees throughout the sample every atom that's present without worrying about whether it's representative or not. So that's, well, I think it's more likely to be robust, but I admit that probably suggestive changes in palladium isotopes have been seen, and maybe that's, I will eventually see that when I finally analyze about 40 or 50 gamma rays and get their ratios. But I haven't done that yet. I just got this data Monday before I got off to this meeting, and so I have a lot of work to do. Thanks for the suggestion.
Dr. Dash?
Are you planning to cross-check by any other technique?
Well, there aren't many other techniques that will see the whole sample, but for example, boron-10 doesn't produce any radioactivity, and so I can't do it by neutron activation. I could, of course, try to do it by the surface analysis methods, the time-of-flight SIMS, and I have started to try to do that, but I'm always nervous that I'm hitting an inactive spot on the sample, and that it would take too long and too expensive to finally march my way all over the sample to be sure.
How much of the surface does the SIM scan?
Well, you can have it be about 40 or 50 microns at a time, I guess.
Well, I don't do the work myself, but the model that does the work for me scans 3 millimeters at
Does it?
3 by 3 millimeters.
Well, I guess it can be done, that's true.
Dr. Chow?
I'm just curious, how much heat did the electrode produce?
0.56 megajoules,
0.56 megajoules.
and that's about 65 megajoules per mole of palladium. And by the way, I was able to measure by the ratio of the gamma rays here, that boron in this particular sample, boron 10 anyway, was 20 parts per million by weight. The total boron was presumably 100 parts per million. A very frequently observed number in palladium, I guess because everybody's always adding it in the final form. I was encouraged to do this one because of Kevin Wolf's results, seeing reactions or apparent reactions at very low levels, but nonetheless fascinating at deuterons and protons on palladium isotope. And so I said, well, if Kevin can get the deuteron into the palladium nucleus, I ought to be able to get the deuteron into the boron-10 nucleus at quite a larger rate because of the lower Z.
Please.
I believe you said that you get information from the initial thickness of the sample, is that right?
Yeah.
Okay, which means then that your fear about the leaching of boron is not really well founded because
Well, I hope you're right.
are only to the surface.
I hope you're right, but it is only 25 microns thick, and it's being leached from both sides. It's immersed, you see.
Yeah.
So I was suspicious that we might have that, but if so, we will check it by having the anode, which is similarly immersed in the same thickness.
In addition, you would believe that the interesting nuclear reaction occurs on the surface only, and then you're diluting your measurement of the initial thickness.
That's right.
Please.
There's always the worry about leaching, but you might be interested that there was quite an interest in making palladium-boron diffusion tubes, including palladium-boron diffusion instead of palladium-silver for electrolyzers. So it certainly doesn't come out there.
It doesn't come out, oh, you mean it doesn't
No, it's stable.
get leached?
That's stable.
Yeah, well, I hope that's true, and I thought I'd better check it, though, because it's a pretty amazing result if it is indeed confirmed. And of course, if boron can do it, many other things perhaps can do it as well. And so we shouldn't restrict ourselves to looking at this one. It just happened to be convenient to look for based on the fact that boron-10 has a 4,000 bar cross-section. And even if it has 100 parts per million, I can readily see it.
Yeah, it has also a big Coulomb barrier.
That's right, the Coulomb barrier.
It's enormous. So
Yeah.
You're not going to use the 4,000 bars.
I'm sorry, what is your comment? I don't
My comment is that yes, the cross section is large, but when you can get there, that you also have a larger Coulomb barrier to go through.
That's true.
Much larger.
Well, again, reasoning by a country boy analogy, if palladium can collect deuterons in Kevin Wolf's case, boron ought to be able to do it too.
Yeah, but then it's not the direct. I think it would not be direct reaction. It would be something final product. So neutral actually, I cannot comment.
Any more questions? No? Oh, yes, Councilman.
Did you measure also the materials without heat production or original?
Yeah, the virgin material was the material out of which we made the cathode, but it has not been used as a cathode.
But my experience is that sometimes you don't, when your method is sometimes it's some other elements or materials containing the material, so be careful to be measured by some neutron activation method.
Yes. So I agree that I'm always subject to contamination by some other gamma rays, other neutron capture, and that's what I was pointing out. I don't get a perfect flat 4-on-10 peak, but rather a slightly peaked one, which is, I already know from literature that there are a couple of palladium capture gammas in there, and they would be diluting the effect and making it conservative rather than, I think, assuming we're not burning palladium.
Okay, thanks, Tom, again.
Okay, thank you very much for all presentation. So this session is closed. We will change.
Thank you very much. Our next session for this morning will be Innovative Approach. We will have 2 speakers here, and the session will be chaired by Dr. Sanchez and Dr. Kanimura.
This session is very short. We have only 2 presentations. The general title is Innovative Approaches. And the first presentation is by Dr. Oriani, and the title is A Confirmation of Anomalous Thermal Power Generation from a proton conducting oxide.
In the 4th International Conference on Cold Fusion in Hawaii, Dr. Mizuno of the University of Hokkaido announced that he was able to obtain a considerable amount of excess power by the use of perovskite oxides bathed in deuterium gas at a temperature such as 400 degrees Celsius. The way he did these experiments was to elevate the temperature by use of a small furnace surrounding the specimen. Heat this in a vacuum first, then introduce one gas or another. Argon or helium or light hydrogen had no effect, but the deuterium gas produced more temperature, measured by some thermocouple, than was expected from the calibration curve and the amount of power that was put into the furnace. This excited me very much because high temperature generation of excess power is much more useful than the same energy generated at low temperature because of the fact that you have a higher Carnot efficiency for the conversion of thermal energy into any other form of energy. So I determined that it would be very worthwhile to verify this effect. I was encouraged in this by the fact that Dr. Beberian in France had also claimed to have observed excess power from another proton conducting oxide, a calcium aluminum oxide system. So the first experiments that I performed, exploratory sort of experiments, were done with an isoparabolic calorimeter in which the operating signal was a temperature rise by a thermocouple, a chromium-ionized thermocouple. And indeed, every now and then I thought that I observed excess power based on the calibration curve. But I could not have any confidence in these results. The reason being that in the asymptotic calorimeter, I found that the response to the thermocouple was very much a function of the spatial distribution of the power generation. I was using both the furnace and an auxiliary heater in order to achieve the required temperature. The calibration was done, in fact, by the use of the auxiliary heater. Now, necessarily, the specimen then would be in a different position from the auxiliary heater. And that was enough to give me a 5-degree temperature difference for the same total input power than I was having in the calibration. If I used only furnace power as the input, that's not very satisfactory. The other problem was that any change of gas phase composition, either purposefully or omitedly, for example, by a leak or by evolution of gases from the furnace ceramic or the specimen, that was enough to change the thermal conductivity of the gas phase sufficiently so the thermocouple would read a different temperature for the same heat input. I was very surprised at this, but the theoreticians here to help me understand why, if I keep the number of molecules of deuterium gas constant and introduce a very small number of molecules of air, for example, nitrogen and oxygen, I increase the number of thermal carriers thereby by the leak of air in or emission of air into the system, but the thermal resistance of the gas phase increases markedly. So the temperature rises and one thinks one has extra power, but that's not the case. For these reasons, I decided that I had better change my calorimetric technique, and I went to the Seebeck or heat flux calorimeter. Operation of a heat flux calorimeter of Seebeck type at high temperature is not easy. I will describe this very briefly. Okay. The specimen is here. No, I think I prefer this. Thank you. The specimen is over here, auxiliary heater over here. Each one is connected to instruments by going through a hole in the bottom supports, insulated supports. The furnace and the auxiliary heater are surrounded by a small furnace, which is fed or supplied by a constant voltage power supply. This is contained inside of a stainless steel jacket, which can support high vacuum or high pressure gas. In turn, that's surrounded by what I call the Seebeck system, or the Seebeck box, and I will show that to you in more detail in the next transparency. Around the Seebeck system, which consists, by the way, of 710, I think, thermocouple junctions distributed over the 5 surfaces of the box. Around that Seebeck box is a copper box whose function it is to smooth out temperature variations as felt by the Seebeck system. The environment of the calorimeter is an air jacket whose temperature is controlled by a separate controller. The constant temperature, a constant velocity fan here to circulate the air, and insulated box, and of course a distributed sensor system and control system to maintain a temperature over here about 106 degrees Celsius. The heart of this system is, of course, the Seebeck assembly, and I'll show you what that looks like schematically. Here is a schematic of the box, which is of the order of about that high and about this wide. And each of these spaces is composed of machinable ceramic insulation, electrically insulating material with perforations made by our machine shop, into which are threaded a wire which is composed of alternate sections of chromel and alumel wire, a very common high-temperature thermocouple material. The threading is done in such a way that on the inside surface of each of these walls and the top of this box On the inside surface, we have one polarity of the thermocouples. I symbolize that by A to C. On the outside, the opposite polarity, C to A. And therefore, these are effectively in series of opposite polarity, one after the other. Therefore, the EMF that is registered by the thermocouple system, which I can call a thermal pile, I suppose, that EMF then is a measure of the temperature gradient integrated across the wall of this box that surrounds all the thermal energy production mechanisms, the furnace, auxiliary heater, and if any magical excess power is being developed, then the EMF from this thermal pile will respond to that. So the measurement consists then, well, first of all, I should say the calibration consists in putting in a measured, carefully measured electrical energy into the furnace and into the auxiliary heater, and measuring the response of the thermal pile, the EMF, which I will call E sub S, or EMF of the CFEX system. I'll show you here a copy, a Xerox copy, of a strip chart recorder, which is used simply to follow the history of both the jacket, the air jacket temperature, and also the CFEX system. The actual measurements are made with digital millivolt meters. You notice that the time scale is large. From here to here, we only have 50 minutes, and the sensitivity is good also. This small division is 1/10 of 1 millivolt, whereas the overall signals are the order of 70 or 80 millivolts. And so this shows you a typical steady response at about 400 degrees Celsius. The jacket temperatures, of course, are very constant. In fact, the environing air, which I call the jacket, has to be very constant because that is used as the heat sink for the power that's being generated internally in the stainless steel container by the furnace control, which maintains the specimen at about 100 degrees C, and by the auxiliary heater, and also by any power furnished in the power runs to the perovskite type oxide. By the way, I failed to tell you that the nature of the perovskite, which has been made for me very kindly by Dr. Mizuno at Hokkaido University, is based on strontium cerium. It's effectively strontium unity, cerium 0.9, and yttrium 0.08, niobium 0.02, and the rest oxygen 2.97. It was necessary to confirm that the CFEX calorimeter is in fact insensitive to the spatial distribution of thermal power. I did that to my satisfaction. It's also very important to confirm that it's insensitive to the gas-phase composition. And this graph shows you two things. First, consider the bottom curve, which is the CFEX signal, E sub S, as a function of input power in watts. The E sub X is millivolts, as you see, 84, 74, and so forth. Input power is 50, 55, 60, and so forth, 75 watts. You notice that even though I have 4 different gases here, I have one curve, one straight line. The open circles are argon at 1 atmosphere. The excess crosses are representing helium at 4/10 an atmosphere. The squares are deuterium at 0.2 atmosphere. And these triangles, of which there are only 2, represent admissions of a very small amount of air into the deuterium, and they also lie in the same line. To be contrasted with the results of the thermocouple temperature, which I also have in the system, as a function of input power, you notice that there are 4 different curves for, there are 3 curves here, but also indication of the triangles of where the oxygen-contaminated deuterium lie. As you see, as I said before, the open circles are argon, the crosses are helium, and the squares are deuterium. So any admission of any leak of air or evolution from the surrounding would damage measurement made by measuring the thermocouple temperature. The operation at steady state is what we need. And at steady state, of course, the power, P, that's delivered by whatever sources of power I have in the system, has to equal the power that's going out to the CPEC system walls. Except that it's impossible to surround the entire plane with thermocouples because I have to have input and output of gases and vacuum as well as the electrical connections. So that there is also a term, not only the thermal conductivity of the walls of the CPEC box times the temperature, the average temperature gradient or difference across those walls, but also terms associated with losses to the bottom of the calorimeter. But we can make these small, and in any case we can calibrate these out, as I indicated before, and that is what has been done. The signal, which I will call E sub S prime, then is found to be a linear function of the input power, no matter how distributed, no matter where it's coming from inside the system. We established a standard deviation sigma for the calibration points, and that's quite important what I have to say after that. And then I schematize here where we have the signal E sub S from the CPEC as a function of power. We establish a straight line. In the power runs done with the deuterium gas, if I happen to obtain at this input power a single E sub S which lies here, north or above the calibration line, then I would say this is excess power. And I calculate how much that deviation, delta, represents in terms of excess power by the very simple equation knowing the slope of this line. And so the deviation, delta, is related to excess power by simply the slope of the calibration line. So what I have to establish is that this deviation is larger than statistical fluctuations or statistical random errors in my calorimetry. I collect here, it's difficult to see, I'm sure. I collect here results of 8 calibrations done with helium and with deuterium in the first column. I'm sorry, in the second column. They're over here. These are simply the number of sigma values, the number of standard deviations that the data points individually deviate from the regression line established for the data. And you notice we have a Gaussian distribution, both positive and negative deviations of the order of, well, the largest is about between 1.5 and 2 sigma values. So obviously I have to have values for my power runs larger than that, otherwise I have no confidence in the generation of excess power. I have collected here the successful experiments, which I call run X, experiment X, and 6 deuterium runs. And you see that the deviation from their respective regression lines, the calibrations, are all very much higher than 0. We have as large as 5.5 to 6 for experiment X, and as large as 7 to 7.5 sigma values. In fact, 2 values for some of the deuterium runs in this style. There were 2 kinds of measurement. One in which the deuterium itself was used as a gas phase for calibration with a specimen out of the system, because earlier work had made me think that in some cases I was getting excess power without even putting it in the DC power into the specimen. I just realized I forgot to tell you one important thing. The method of making these measurements is we hold the specimen at high temperature with a furnace, and then we put in an alternating DC current into the perovskite. The perovskites at these temperatures are only proton conducting, very low electronic conductivity, and vanishingly small ionic conductivity of either cations or anions of the oxides. And the Mizuno method experiment, which I'm trying to verify, was in fact done by this kind of alternating direct current at frequencies of the order of 0.01 to 1 hertz, I think, something of the sort. No, 10 to minus 3 hertz to 0.1 hertz. Slow alternation of the polarity of DC current. I will show you the magnitude of those DC powers into the specimen in a minute. But I just want to give you a survey of the results that in the power runs, essentially all of, except for one, are above the zero of the deviation, and they deviate by large values, large values of sigma. But let me give you some details of these. The larger number of experiments were done with helium calibration. But first I will show you using deuterium calibration. I have here the input power of the alternating DC into the oxide specimen. The radius from 0 to largest amount, in this case, 0.047 watt. The voltage supply was of the order of 30 volts. The second column gives you the total power, which is to say furnace power plus the DC power to the oxide. And the values range from 65 to about 68 watts. The third column gives you the measurement of the signal from the Seebeck system in millivolts, order of magnitude 70 or 80 millivolts. The fourth column gives you the duration of the episode in hours, episode meaning the period during which excess power is being generated, as observed by this deviation in this column. The deviation from the calibration line, delta, they range from 0.11, which is no excess power whatsoever, to 0.64, 0.66. And the last column is the number of sigma values that these deviations represent. As you see, they range from unity, which is of course no excess power whatsoever, to about, in this case, about 5.7, 5.6 sigma values. And if I make a different kind of plot to show you what that looks like, I have here, okay, 2 minutes? Two kinds of symbols. The open symbols, the open circles represent results where 0 DC power is furnished to the specimen, and the filled circles where finite DC power. And the points above the 4 sigma deviation from the regression line for calibration, I feel fairly confident that we have indeed real excess power being developed by the prospect. Magnitudes, well, as you see, 0.4, 0.6, 0.8 watt. I suppose one can say that for the case of the open circles, we have an infinite ratio between the excess power and the input power into the specimen. But you can think about that as you wish. Using the same specimen and another kind of calibration and then power runs, I have these results. Again, the same kind of tabulation. The last 2 columns give you the deviation in millivolts and the number of sigma values from the regression line for the calibration. And in this case, we had as high as 7.3 sigma values. And again, I can make that same kind of plot as I showed you before. That all values above 4 sigma, I can be very confident are in fact excess power. The rate of success is very, very low, both in Mizuno's hands and in my hands. I have a rate of success of the order of 10%. That is to say, in one experiment after the other, perhaps only 1 in 10 will give you any excess power. And I'm showing you here 2 successful runs out of about 15, I think. Very recently, after I submitted this work to the Journal of Fusion Technology, the paper will come out in November this year, I had another run, and I'll show you this, even though it's only a marginal successful run, because it perhaps will clarify for you some of the points that I've raised and the techniques that I use. Here is the calibration curve. The X's are in fact power runs. The calibration curve has a sigma value of the order of 0.08 millivolt. And this band represents, therefore, 2 sigmas, both above and below the line. The interesting power points are the X's over here. And you can see 3.6 sigma value for this one, and this one 4.1 sigma value. I call that marginal. It looks okay, but I prefer to feel that. I just show you this because this shows you exactly how I've done things. These experiments are continuing. Hopefully, Dr. Mizuno will be able to analyze by his techniques specimens that have produced excess power and compare those to those which have not. That remains to be done in the future, and we hope to have some success in that area. So thank you very much.
We are open to questions. Yes, Tom, please.
Dick, what is the life-limiting factor that commonly shuts the thing down?
Either I change the conditions myself because I wish to explore some other power level, or it does slowly go down. But I don't know what are the factors that cause this to happen. The interesting thing is that I've used one specimen which succeeded a second time in producing excess power, where it also succeeded in my first experiment several months behind, back of that. But that's the only case that I know. Only one specimen that I've many have supplied me by Israel.
The longest run was about 23 hours, as I remember seeing your...
Yeah, something like that. That's right.
Thank you.
Does it turn on immediately? Is there any incubation? There's nothing, right? It just loads right away.
No, it does turn on immediately. Usually after I make a small change in the heat input or in the temperature of the specimen, but I really cannot say what are the conditions for turning it on.
Right, well, it really is effectively like a zero loading type situation. There's no...
I'm sorry, zero loading?
Zero loading.
I don't know what you mean by zero loading.
It doesn't.
This is bathed in deuterium gas.
Yes, I know that.
And I turn on the alternating DC power.
Right,
DC
and that's what I was thinking, so it's just sort of...
And then after that, I wait a while, and it may take a day.
It may take a day.
It may take a day, it may take a small number of hours. And then again, it may necessitate a change of temperature in order to get this thing going. And very often, as you see in the open circles, I turn on the DC power, and then for many hours after that, I continue to get excess power.
For many hours?
After that, I continue to get excess power. Yes.
Okay. Are there any other questions or comments? Yes, please.
Professor, have you any correlation between the anomalous thermal behavior and the current passing through your sample?
No. I have had such small number of successes that I cannot make any statement about that. My feeling is that I need a certain amount of amperage going through the specimen, by the way, it is in the order of milliamperes, in order to see any excess power, but I do not really know. I have to do much more work if I can establish anything like that. I do not know.
Thank you.
Just one more.
If you have done any experiment in light hydrogen system?
No, sir. No, nothing with light hydrogen as yet. Mizuno did that, as you know, and he observed no excess power. But on the other hand, we do many, many experiments, as is necessary to do with deuterium to get a successful result every now and then. It may be that we will observe excess power. At this point, I do not know.
Okay, and second more.
Yes, when you have a sample that works, can you reuse it later or just use it once?
These two successful experiments, the details of which I have showed you, are from one specimen.
So can you do it 10 times, 100 times, I think?
I've only done it twice for that same specimen. And of course, each time, each experiment lasts a week and a half or so, and I have many episodes of excess power development, interspersed with episodes of zero power development. So what I can say is that in 2 separate experiments separated by months, one specimen did in fact succeed in giving the excess power. The others did not, except this last one, this marginal result that I showed you.
Okay, thank you very much.
Proton conductors, conductivity, structure, photon traps, phase transition with heat and neutron angle. With the assistant Dr. Sangin and Ms. Wabina, translating in English. Please.
Последует примеру, впечатляющим примером. Доктора Рейкина Тойш делают впечатление только на русском языке.
I'm going to read my report in Russian, following the impressive example of Dr. Rikina Toya at yesterday's banquet.
Наши исследования с протон-проводящими керамиками
Our experiments on proton-conducting ceramics show that both nuclear and stable excess heat effects are being observed within these systems.
Наши исследования показали, что эти эффекты
Our research into strontium cerium-03 or barium cerium-03 proton-conducting ceramics showed that both thermal and radioactive effects within them are connected with peculiarities of their structural and electric properties. The analysis of this correlation allows one to assume that ceramics can be successfully viewed as an excellent object for the study of phenomena mechanisms, traditionally termed as cold fusion.
Какие на сегодня существуют положительные результаты по керамикам на основе церата стронция?
So there are positive results of experiments using high temperature proton conductors based on doped strontium cerium-03 or barium cerium-03 ceramics.
С палладиевыми и платиновыми электродами.
With palladium or platinum electrodes.
Ядерные эффекты наблюдаются в атмосфере дейтерия.
So the nuclear effects observed and deuterium-2 atmosphere. These are neutrons
И трансмутации.
and transmutations.
Также существует эксцесс хит
There is also excess heat
в атмосфере дейтерия,
in the deuterium-2 atmosphere,
но также и в атмосфере водорода.
but also in the hydrogen-2 atmosphere.
И только что вы слышали доклад профессора Рейка.
And we have just heard Professor Oriani's report.
Нейтронные измерения.
Neutron measurements.
Пожалуйста, первый слайд.
First slide, please. The samples were prepared.
Образцы были приготовлены в виде дисков.
The samples were prepared in the form of discs. Next, slide 2, please.
Это нейтронный детектор.
This is the neutronic detector.
Здесь два кольца.
There are 2 rings of counters there.
Это ячейка.
This is the cell. Slide 3, please.
Это ядерная электроника.
This is nuclear electronics.
Мы использовали Common стандарт.
We have used the common standard.
Следующий.
Slide 4, please.
Это установка.
This installation.
Это защитный домик.
And this is the shielding box.
А это ячейка электрическая.
And this is the electrochemical cell.
Еще раз экспериментальная ячейка.
So the experimental cell once again.
Детектор.
the detector
электрохимический чип.
and the electrochemical cell.
Это расположение образцов в чипе.
This is the sample's position within the cell.
Наша электроника позволяла следующие практически измерять.
So our electronics allowed us to measure the following characteristics.
Это амплитудный спектр,
The amplitude spectra,
временное распределение событий
the time distribution of events,
и распределение временных интервалов
and the time distribution of intervals
между двумя последовательно зарегистрированными электронами.
between two successively registered electrons,
Здесь постоянный нейтрон.
neutrons,
Здесь постоянно 4 микросекунды.
with a constant being 4 microseconds.
Один из результатов
One of the results obtained
с ратами Стромса.
with strontium serate.
Вот это фон,
This is the background,
а вот это нейтронная вспышка.
and this is the neutron burst.
Ее длительность порядка сотни микросекунд.
Its length about
100.
100 microseconds. It was established that for reliable analysis, it is necessary to consider pulses in the range from 31 to 122 channels in the amplitude distribution. The rest part may be connected with detector noise, electronic hindrance, electric and acoustic signals.
В этих экспериментах, в серии экспериментов во время охлаждения образца
In a series of experiments during cooling of solid
комнатной температуры
electrolytes to room temperature, after
время
its
электронных
electrolysis in deuterium atmosphere,
в процессе охлаждения нагрева
and thermal treatment by cooling heating,
наблюдалась нейтронная вспышка.
the pulse count rate was observed as follows.
Время между двумя нейтронами, ближайшими по вспышке,
The time between the two neutrons in the burst
меньше 20 микросекунд.
less than 20 microseconds.
Измерение тепла.
Excess heat measurements.
Установка по калориметрии нами была описана в материалах Монте-Карло.
The method was described earlier in the Monte Carlo proceedings
Там записана калибровка.
and the calibration too.
Какие выводы основные? Что эксцессы хит существуют устойчиво.
So excess heat exists
Значит, эффекты порядка
of the
0,02 ватта.
of the order of 1.02 watts.
Лучший результат был 1032%.
The best result being 1032%
Эти эффекты ниже
for deuterium.
Эти эффекты значительно ниже для
And
водорода,
these
чем
effects being lower for hydrogen 2 than for deuterium 2.
параллельно мы проводили микрокалориметрию.
So microcalorimetry has been carried out
Там следующий результат,
parallelly.
что
Has
процессы,
obtained the following results.
процессы как импульсного выделения тепла,
Both processes of input of heat pulses and decay of heat take place during loading by electrolysis in dome samples.
также наблюдается нормальное
Abnormal heat spike-like behavior
импульсное
is
выделение.
also observed.
Эти эффекты тоже больше для deuteria, чем для водорода.
These effects too are greater for deuterium-2 than for hydrogen.
Вот еще примеры некоторых типичных результатов.
So here are the examples of some typical results.
Для постоянного тока
For direct current,
эффекты порядка
the effects being
20%.
of the order of 20%.
Для реверсивного тока
For the reverse electric current,
эффекты порядка
these
excess heat
effects
порядка 200%.
of excess heat being of the order of 200%.
Эти эффекты могут быть скоррелированы с проводимостью.
These effects may be correlated to conductivity.
Вообще эти керамики имеют
The experimental studies of conduction of electrolytes, such as strontium cerium 03 or barium cerium 03 based doped ceramics, are summarized as follows. A1.
при комнате свободной от атмосфере диоксиды имеют электронную типа проводимость.
Has three-type conduction in atmosphere free from hydrogen.
В водородной атмосфере
2. In hydrogen atmosphere.
они испытывают чистую протонную проводимость.
They exhibit pure protonic conduction at temperature of 500 to 900 degrees
Проводимость
centigrade.
порядка 0,01.
The conductivity is of the order of 0.001 to 0.01 Siemens per centimeter. 3. The protons are formed as a result of the following processes.
Однако в проводимости существуют особенности,
But there are some peculiarities in conduction
которые могут быть очень важны для механизма холодной синтеза.
which may be extremely important for the explanation of cold nuclear fusion mechanism.
Только один пример, хотя таких примеров много.
I have only one example, although these examples are numerous.
Вот результаты исследования изотопного эффекта для стронция цериум-3
There are the isotope effect results for strontium cerium 03.
показывают, что протонные прыжки
These results show that proton hops cannot be viewed without taking into account the interaction with lattice environment.
и, может быть, это взаимодействие, оно как раз ядерное, может привести к проявлению аномальных эффектов.
And maybe this nuclear interaction may lead to anomalous effects.
Структура. Что касается структуры.
Structure and structure changes. This problem is more complex in character than it seems. We conducted the analysis of X-ray structure data both pre and after experiment with the samples by drone-free diffractometer. Our X-ray study shows that the sample based on strontium cerium 03 has the orthorhombic structure. Some indications exist that the structural modifications of the lattice
Во время
can
термоциклирования
take place during the thermocycling, when phase transitions are also
это все
considered.
может приводить к очень сильному изменению распределения дейтерона.
This can drastically affect the deuteron distribution,
Расщеплению дейтеронных позиций,
the splitting of the deuteron positions, and the migration. This can have a direct influence
на результат холодной синтеза.
upon the non-reproducibility of polynuclear
Самые последние эксперименты показали,
The latest experiments show that the samples used in experiments on heat and neutron detection have several structural changes,
что в этих экспериментах это сильно изменилось. В частности, как пример, вот образец на основе церата стронция,
which gave an insight into the mechanism of the processes. A sharp decrease of the volume of the elementary cell of the sample,
значение 314,9 ангстрема кубического.
generating heat pulse, has been found by X-ray method. As an example of the strontium cerium 03 based ceramic characterized by excess heat, has the value of has this value.
Изменился 314,9 ангстрема кубического. В начале эксперимента.
Yes, being 314.9 angstrom at the beginning of the experiment.
И 313,8 ангстрема кубических
To
после эксперимента.
313.8 cubic angstrom after the experiment.
Диоксидный бронз, эти результаты еще более значительны.
For oxide bronzes, these results are more considerable.
Мы нашли изменение объема
We have found volume changes
в тех образцах, которые показали нейтронные эмиссии.
in samples which have shown neutral yield.
Вот первая таблица это для опытов с положительным результатом.
This table is for experiments with positive results.
В тех образцах, где не было эффекта,
Within the samples where there was no effect,
такого изменения не было.
there was no such change.
Керамики как модельный объект холодного синтеза.
Ceramics as model object for cold fusion.
Здесь только несколько примеров скажу. Фазовые переходы.
There are only a few examples here. Phase transitions.
Роль фазовых переходов активно обсуждается в классической схеме клеевого конкурса с палладием D.
The role of phase transition is actively discussed with classical scheme pertaining to palladium D.
Однако керамика.
But for cold fusion with protonic conductors, the influence of these factors are taking new twists.
В частности, во время этих исследований нами было обнаружено существование новых фазовых переходов.
So during these experiments, we observed the existence of new phase transitions.
И выделение тепла как раз коррелирует с прохождением этой точки.
And excess heat correlates with passing of this point.
Протонные ловушки.
Proton traps.
В последнее время активно обсуждается также роль протонных захват частиц в механизме холодного синтеза.
A model of multi-body fusion for deuteron clustering exists for palladium-deuterium systems, which looks supportive for some experiments. The problems of particle traps in palladium-deuterium also have aroused considerable interest.
Эксперименты 1995 года Хэмпелмана.
The experiments of the 1995 year
Показали по квазиупругому рассеянию, нейтронному рассеянию.
As regards quasi-elastic neutron
На
scattering
цератах стронция.
upon strontium serrate.
Показали, что на самом деле в цератах существуют протонные ловушки радиусом 2,6 ангстрема.
That proton traps really exist within protons.
В образце.
Within proton samples, within the samples.
Ловушки с радиусом
The traps with a radius of 2.6 angstrom can immobilize the protons.
Теперь относительно образования трещин.
Crack formation.
Во всех наших опытах с положительным результатом
In all our experiments with positive results,
мы обнаруживали интенсивное образование трещин.
we observed intensive forming of cracks. The intensive crack formation on the ceramic sample has been observed in all our experiments showing excess heat.
Это может быть связано с процессами сильного сжатия решетки.
This can be due to the compression, to the structure changes,
существованием ударных волн.
or to the existence of shock wave in the sample,
Иногда
which
даже образцы рассыпались в пудру.
sometimes the samples were collapsing into powder.
Еще в заключение об одном интересном эффекте, который мы наблюдаем.
And in conclusion, I want to speak about one more interesting effect which we observed.
Во время эксперимента
So during the experiment,
показали
so our investigations of neutron emission
показали влияние нейтронного фона на выход нейтронов.
have shown the influence of background on yield of neutrons from ceramic.
Более того, во время электролиза в атмосфере deuterium
Furthermore, during electrolysis and deuterium atmosphere, dependent from conditions and the chemical purity of ceramics, we have observed new neutron anti-effect.
как до начала, так и после эксперимента измерялся нейтронный фон.
Both before and after the experiment, we have measured the background during 2 days.
И во время термоциклирования наблюдались сильные изменения нейтронной части.
But at thermocycling, the abrupt changes in neutral country were fixed into the shielding box with the cell. Typical situation. This decay appears near the points of phase transitions and lasts a few tens of seconds, followed by neutron bursts. Analogous effect has been observed in the experiments with molten salt according to our method, which was described earlier. The nature of this phenomenon is yet to be investigated.
Интересно, что как раз вот во время этой точки
It is interesting to know that just in this point
около фазового перехода
of a near phase, close to phase transition,
и наблюдаются тепловые эффекты.
we observe all the thermal effects. Thank you.
I want to know the background neutron level in the last figure. The last figure. Neutron level. Yeah, neutron level.
The neutral background amounts to 0.008 neutrons per second.
And how the peak in the figure is high compared with the background neutron?
Дело в том, что за такими провалами иногда как раз и следовала вспышка электронов.
The fact is that just after this decay, the burst itself followed.
Поэтому это может быть как раз пик связан с электронами, повышенными электронами.
Maybe this peak is connected with the neutrons' higher emission.
Но может быть это происходит задержка электронов.
But maybe it's simply because the neutrons delay is taking place within the shielding box.
How many neutrons can you tell in one peak?
В максимальном пике, который мы наблюдали, в процентном событии.
Within the maximum peak which we have observed, we have counted 25 or 21 even.
На обычном месяце.
But commonly it is much less.
How many? How many?
21.
21 neutrons in
21.
one peak. Thank you.
But heat is not correlated to neutrons. This is Mr. Sankey's opinion.
First, I would like to congratulate you on a wide range of interesting experiments in this area.
Thank you very much.
And I would ask, did you see any difference in behavior when you used palladium electrodes instead of platinum electrodes?
Yes, we did.
Could you tell us what these differences were?
Пока вот сейчас надо быть очень осторожным, чтобы здесь делать заключение.
One must be very careful to draw any conclusions.
Но, по крайней мере, такое впечатление, что она чувствуется, да.
But there's an impression that this difference is strongly felt.
Она сказывается и на тепле,
It produces its effects upon heat and the neutral counts.
но иногда бывают результаты с одними электродами, которые превышают эту разницу между
But sometimes the results with certain electrodes exceed the difference between these two materials.
Thank you. Now, when you made your experiments with deuterium, did you use heavy water in order to insert the deuterium in the sample, or did you use light water and then put a deuterium environment outside the sample?
Will you please say it again?
Yes, he did some experiments with deuterium instead of hydrogen. In the case he used deuterium, was this inserted in the ceramic with heavy water?
Мы делали свои эксперименты, о которых я рассказывал, это в атмосфере газа.
We made our experiments in gaseous atmosphere.
Естественно, такие эксперименты можно провести в атмосфере тяжелой воды.
One can naturally carry out these experiments in the background, in the atmosphere of heavy water.
I ask this because the transport inside the ceramic is determined by the hydrogen species that is put into the ceramic during its preparation.
Yes, of course, you are right.
Thank you very much.
Oh, the only one.
According to your abstract, the normal phase is orthorhombic at 445 degrees centigrade. Do you know what the phase transition is? Were you able to measure the crystal structure? And is there a volume change associated with the phase change?
Will you please say it again and with pauses, because it's hard. Mr. Sampian has difficulty in understanding English.
I'm sorry. According to your abstract, the normal phase is orthorhombic at 445 degrees centigrade. What can you tell us about the phase after the transition above 445 degrees?
Да. Я могу сказать, что это переход, ну, во-первых, это переход, такой переход был обнаружен впервые в нескольких работах, как в России, так и, например, в Италии, только в прошлом году.
Firstly, such transition was observed for the first time by researchers 2 years ago.
Поэтому сейчас здесь тоже однозначно исключить сделать нельзя. Но похоже, что это структурный фазовый переход выше симметрии решетки. То есть симметрия меняется.
It seems that one can jump at conclusions now, but it seems that the latest symmetry is being changed to a higher symmetry.
Но это только предварительное указание.
But this is a preliminary consideration. Those are my preliminary considerations.
Okay. Time is over. Thank you, Dr. Sang-Ging and Liz.
Thank you very much. We will take a lunch break now until 2 o'clock. The afternoon session of excess energy nuclear products will start at 2. And this will be followed by the final summary of the conference. And also I'd like to remind you once again to please submit your proceedings by 2 o'clock. Thank you.